This video I am going to discuss about electric field due to uniformly charged thin spherical cell. Let us consider a cell of radius capital R and center is O, and suppose a charge plus Q is given to this spherical cell, so that charge is uniformly distributed throughout its surface here. And for this cell, its surface area is 4 pi r square. This is the surface area of this spherical cell of radius r, capital R, and charge given to this cell is Q. So its surface charge density, which is sigma, and that sigma is charge per unit area, means Q upon 4 pi r square. So this one is surface charge density, sigma is equal to Q upon 4 pi r square. So dear student, our aim is to find the electric field intensity due to this charged spherical cell at any point outside the cell, at any point inside the cell, and finally on the surface of cell. So for this purpose, let us consider a point P at distance small r from O. At distance small r from O means here when small r is greater than capital R, so that point P lies outside the cell. When small r is equal to capital R, then this point P lies on the surface of cell. And when this small r is less than capital R, then that point P lies inside the cell. So our aim is to find electric field at any point outside the cell, on the surface of cell, and inside the cell. So for this purpose, suppose I am taking a point P at distance small r from the center of the cell, where electric field is to be determined. And remember this point P lies outside the cell. And as you know, first we will draw a Gaussian surface concentric to this spherical cell and passes through the point P. So this one is what here? This one is a Gaussian spherical surface which passes through the point P. This one is a Gaussian surface. And first we will calculate what is the electric flux passes through this small area element taken on this one. And finally, for finding the electric flux through entire Gaussian surface, we will integrate it. So first our aim is to find electric field at point P, and that point P lies outside the cell, so that one is at an external point. Let P be a point distant small r, and here that small r is greater than capital R, means that point P lies outside the cell from the center where the electric field is required. So first we draw a Gaussian surface passing through the point P, and let us consider a small area element on this Gaussian surface, and the area vector is dA outside, and the electric field due to this charged spherical cell will be also goes radially outward. So here electric field will be also outward. So electric flux through a small area element, area element means through this small area. What you will write? d phi e is equal to vector E dot vector D. And vector E dot vector dA, here electric field and area vector both are parallel. So angle between them is how much here? 0 degree, means both are parallel. So for finding the electric flux through entire Gaussian surface, we will integrate it. So the electric flux through entire Gaussian surface means entire outer Gaussian surface. How we will get? Integrate d phi e is equal to whole integration of vector E dot vector D. And as you know, integration of d phi is phi e is equal to, you can write here vector E dot dA, E dA cos 0, and which is equal to whole integration of vector E into dA. So phi E is equal to, you can take E outside, and here whole integration of dA. Whole integration of dA means total surface area of this spherical cell, and whole integration of dA becomes E into 4 pi r square. So phi E is equal to E into 4 pi r square. But by Gauss theorem, phi E, electric flux passes through this whole Gaussian surface, is equal to, now you look here, this outer Gaussian surface is completely enclosed this original spherical cell. And what is the charge on this spherical cell? Q. So you can say this Gaussian surface is enclosed this charge Q inside it. So you can say phi E is equal to Q upon epsilon naught. And from these two here, phi E is equal to E into 4 pi r square, and phi E is equal to Q upon epsilon naught. Both will be same. So you can say E into 4 pi r square is equal to Q upon epsilon naught. And from here you can say E is equal to Q upon 4 pi r square epsilon naught. And also which you can write here 1 upon 4 pi epsilon naught Q upon r square. So dear student, you are getting here electric field at any point outside the charged spherical cell is equal to 1 upon 4 pi epsilon naught Q upon r square. This one. And you know, already have derived, this is the expression for the electric field due to a point charge at distance r from it. It means in the case of a spherical cell, when you will consider any point outside the cell, so for that point you can assume whole charge given to this spherical cell can be assumed to be concentrated at its center. But don't think here that this charge is lies at center. You can assume it like this one here. So this is the expression for the electric field due to a charged spherical cell at any point outside the cell. And also, you know, already I have told you surface charge density sigma is equal to Q upon 4 pi r square. Means charge given to this surface, original surface, Q, surface area of this cell, 4 pi r square. So you can say sigma is equal to Q upon 4 pi r square. So from here Q is equal to 4 pi r square into sigma. So same expression can be also written as E is equal to 1 upon 4 pi epsilon naught. At place of Q you can write 4 pi r square into sigma. So 4 pi r square sigma upon small r square. Now this 4 pi is cancelled by 4 pi, and you can write E is equal to sigma upon epsilon naught capital R square upon small r square. So the electric field at any point outside the cell, either this one or this one. This one is given in terms of the surface charge density, and this one is given in terms of the charge given to that spherical cell. And for finding the electric field at the surface of this spherical cell, simply at place of small r, we will write when small r is equal to capital R, then this point P is lies on the surface of cell. So simply in this formula, at place of small r you put the capital R, then you will get the electric field at the surface of this spherical cell. So when you put small r is equal to capital R, then electric field E becomes 1 upon 4 pi epsilon naught, and here at place of Q you write here Q, and place of small r you can write here capital R square. This one, And also you can write, or in terms of surface charge density, you can write 1 upon 4 pi epsilon naught. Here 1 upon 4 pi epsilon naught. This one you can write here, or simply at the place of this one direct you can write from here, E is equal to sigma upon epsilon naught, and at place of a small r, this one is capital R square, and here at place of a small r also write down capital R square. So both is cancelled. You can write here sigma upon epsilon naught. So at the surface of the spherical cell, you can write E is equal to 1 upon 4 pi epsilon naught Q upon capital R square is equal to sigma upon epsilon naught. So in this way we can find the electric field due to a thin charged spherical cell at any point on the surface of cell. Now our aim is to find the electric field due to this charged spherical cell at any point inside the cell. Suppose P dash is a point inside the cell and whose distance from the center O is small r. It means in this case this small r is less than capital R. So this point P lies inside the cell. And like the outside, again when you will calculate the electric flux passes through entire small Gaussian surface inside the cell. So again you can write that one is given by phi E is equal to E into 4 pi r square. Same way, when here you will take small r, then already have calculated phi is equal to E into 4 pi r square, and here I am taking this one is small r. So same way also you can find the electric flux passes through this entire Gaussian surface which is passes to a point P dash is given by this. But by Gauss theorem, you know, this one is a Gaussian surface and all the charge lies on this spherical cell lies on its surface. So inside this Gaussian surface no charge lies inside it. So you can say by Gauss theorem phi E is equal to Q upon epsilon naught is equal to 0, because here Q is equal to 0. Q is equal to 0 means this Gaussian surface does not enclose any charge inside it. Whole charge lies here. So no charge be enclosed by it. So phi E is equal to 0. And from here you can say from both to E into 4 pi r square. E into 4 pi r square is equal to 0. It means this electric field E is equal to 0. What conclusion you get here? Electric field due to a charged spherical cell at any point inside the cell will be always 0. It means the electric field at any point, I am not saying any particular point, the electric field at any point inside the cell will be always equal to 0. So when you will draw a graph between electric field and distance from the center of this spherical cell, then what will be the nature of this graph? You know, O is a center, suppose this one here, and electric field at any point inside the cell will be 0. It means from center to up to the surface here in this region electric field will be always 0. No electric field in this region here. At the surface this electric field is E is equal to 1 upon 4 pi epsilon naught Q upon capital R square. E is at the surface E is equal to 1 upon 4 pi epsilon naught Q upon capital R square. It means at the surface of this cell this electric field will be maximum, and as we go away from the surface then again this R increases, and when this R increases then you can say electric field is decreases. It means as we go away from the surface then again the electric field is decreases. E is inversely proportional to R square. So inside the cell electric field is 0, At the surface of cell, electric field will be maximum, and beyond this cell, the electric field is inversely proportional to R square. So this is the expression for electric field due to a uniformly charged thin spherical cell at any point outside the cell, on the surface of cell, and inside the cell. So dear student, once you go through all the derivation which I have given to you, and also you look the graph properly. Thank you.